الله الرحمن الرحيم. Hello everybody, this is a new video on continuity of function and differentiability of real functions. Actually, this is an exercise, a very simple one, but the main of this video is to explain how we can study the continuity and then the differentiability of a real function. Is there any steps to follow, and how we can deal with this kind of questions? In general, the question is study the continuity and the differentiability of the following function on its domain of definition, or study and precise the domain of the continuity and differentiability of this function. This is the kind of question that can we ask. The first step to study the continuity of function or the differentiability of function, we start sure by the continuity, because if a function isn't continuous on a point or an interval, it cannot be differentiable on that at the point of that interval. So the domain of definition of this function, domain of definition of df index p is equal to r. This is a function, it's equal to sine x over x power p, x less than 0 and p is in z. 1 if x is equal to 0, and a is x squared plus b if x is positive. A, b are real numbers. So the domain of definition is R. Let us study the function on R. The second point to study the continuity of this function, the continuity of f and xb can be done using the following remark. Here what we have? We have two kinds of sub-interval or subdomain of R. We can distinguish the first domain is when x is less than 0. This domain is of the same nature if x is greater than 0. Why? Because they are interval. Both of them is an interval. And in this case, we can use a magic phrase that it says, we can remark that if x is less than 0 or if x is greater than 0, we can remark that this is the question of elementary continuous function, which is sine x and x power p. If x is greater than 0, this is a very continuous function. It is well known that is this a polynomial which is continuous, differentiable, and so on. The magic sentence here is to say that when x is less than 0 or x is greater than 0, I mean x different of 0, in this case we can say that for x different than 0, fp is a question or elementary functions which are continuous. So fp is continuous using the algebraic rules of continuous function. I mean product composition, division, addition, and so on. Now let us focus on the special point or points. In this case we have just one point. In other exercise it can be more than one point. The special point here is for x equal to 0. Let us discuss this case. To be continuous at x equal to 0, we have to use the definition. The definition says that the function f is continuous on a point if the limit from the left is equal to the value of the function and it is equal at the same time with the limit of the right. Let me remind that we cannot study the continuity of a function if it is not defined at this function, at this point. So, not like the limits of function, it is sufficient that the point can be at the ends, a limit point, then we can study the limit. We can try to find the limit if it exists or not. For the continuity of function, the function must be defined at the given point to be able to study the continuity and the differentiability, by the way. So in this case, f of 0, it's given, it is equal to 1. From this side, the limit of f of x, it means that the limit of sine x over x power p, the limit, when x goes to 0 from the left. In this case, it cannot be equal to 1 except if p is equal to 1. This is a so famous limit. The limit of sine x over x when x goes to 0 from the left, this is equal to, if p equal to 1, this is equal to 1. If p equal to 0, this is the limit of sine x when x goes plus infinity, undefined. Undefined. This is an undefined limit. Since x1 x goes to it goes to 0, not to plus infinity. Sorry. If it goes to 0, so sine 0, this is equal to 0. If p equal to 0, if p is less than 0, strictly less, so we keep this here, and it goes also to 0. We can write here, we can write it goes to 0 if p is less than or equal to 0. And if x is greater than 1, strictly greater than 1, we can find here plus or minus infinity. It depends on the parity of p, the parity of p. From the right, the limit, from the right, the limit of f of x is equal to, when x goes to 0, this is equal to b. So the unique case on the unique case that is continuous, the function is continuous at x equal to 0, is actually when p equal to 1 and b equal to 1. So if b is equal to 1, in this case, if we take b equal to 1, it will be continuous, and from the left and from the right, so it is continuous. If b is different of 1, or if p is different of 1, in this case the function f p isn't continuous at x equal to 0, but it is continuous out of this point. To study the differentiability, we can study the differentiability on all the point x which are different of 0 for any given p and b. But we cannot study the differentiability of this function at x equal to 0 if b and p aren't equal to 1. So in general, if x is different of 0, f prime of x is equal to cosine x power p minus x power p minus 1. Here we have p sine x if x is less than 0 over x power 2p, and it is equal to 2ax if x is strictly greater than 0. And for x equal to 0, we have not the derivative, so we cannot define the derivative, because actually f isn't continuous. So if it is not continuous, it cannot be differentiable. And what we can say for the differentiability, we use the same magic phrases. We say that f is the quotient of differentiable function and a polynomial, so it is differentiable, and we can write like this in general about functions. To study the differentiability at 0, the unique case is when p is equal to 0. Here p and p is different of 1. Sorry. For p equal to 1, the function takes the form for p equal to 1 and b equal to 1. The function f1 of x takes the form, takes sine x over x if p for x less than 0. It takes 1 if x is equal to 0, and it takes the form plus 1 if x is greater than 0. To calculate the derivative, to try to find the derivative, we should use this definition: the limit of f of x minus f of 0 over x minus 0 when x goes to 0. And since the function is defined differently from the right and from the left, so we calculate the two limits. If they are equal, we can say that the function is differentiable and the derivative at this point is equal to the common limit. From this side, from the left, it is equal to sine x over x minus 1 over x. This is equal to sine x minus x over x squared. 1x goes to 0 minus 1x goes to 0 minus. This actually goes to 0. 1x goes to 0 minus. And from the right, this one, from the right we have, this is the limit of ax squared plus 1 minus 1 over x. 1x goes to 0 plus, and this is also, it goes to 0. So in this case, the derivative exists and is equal. The derivative exists and is equal to let me write it here. f prime 1 of x, this is equal to this derivative, so cosine x times x minus sine x over x squared. For this case, if x is less than 0, it is equal to 0 if x is equal to 0, and it is equal to a x if x is greater than 0. Is it continuous, the derivative? When x goes to 0, it is equal to 0, so it is continuous at the right hand of 0. When x goes to 0, from here we have cosine x over x minus sine x over x squared. So it is not it cannot goes to 0 in this case, and since it cannot goes to 0, quickly we have this approximate. So we lost this one, and we have here this. In this case, we get 1 over x minus x over 2 minus 1. Yeah, that's okay. It goes to 0, so here we have minus infinity, so it's minus, so it is not continuous. Okay, the derivative, it is not continuous, so we cannot say that f1 belongs to c1. We can say that f1 is differentiable, but it is not in c1 on R, since it is not continuous at 0. Thank you very much. See you next time.